Determine the convergence of the series and go from 2 to infinity of 1 over n times ln of n squared. If we want to use the direct comparison test, we first need to come up with a good inequality. We can start building one. First, we observe that ln of n is greater than 1 for n starting at 3. Remember that even though n start with 2 in this series, but we don't need to have strict inequality for the first finite number of terms, so we can start with any n we want. We know that ln of e is 1, but e is less than 3. So we know for sure that ln of n is greater than 1 if n is greater than or equals to 3. We then square ln of n, and we see that we still have ln of n squared greater than 1. And the reason why we use ln of n is because ln of n is an expression in the given series. To have n times ln of n squared showed up, we would multiply both sides of this inequality by n. We have n times ln of n squared still greater than n, because remember that n is a positive number. Taking the reciprocal of these, we have 1 over n times ln of n squared is less than 1 over n. This is one inequality that we came up with, but it is useless. We cannot use this inequality because we know that the series 1 over n diverges. And to conclude that the series that we compared it with is also divergent, we need this series to be greater than a divergent series. In this case, if the corresponding that we compare to is smaller, with the terms less than the term of the divergent series, nothing can be said. If this does not work, perhaps we just need to come up with another inequality, as long as it is a good inequality. Next, we start with ln of n less than n at some point n on. We then square both sides of this inequality to get ln of n squared less than n squared. And then we multiply n to get n times ln of n squared less than n cubed. Taking the reciprocal, we have 1 over n times ln of n squared greater than 1 over n cubed. And we see that the series 1 over n cubed converges because it is a p series with p greater than 1. But this is also useless because in order to say that the corresponding series that we compare to is also convergent, it has to be smaller than the convergent series. So in this case, we end up with a not so useful inequality. This is typically the case when we determine the conversion of the series. We need to try different strategies. We use the direct comparison test, and it doesn't seem to give us a good inequality so that we can compare the two. Perhaps we can use some other method. Observe that if we let u be ln of n, or u be ln of x, the derivative of ln of x is 1 over x, so this is a good candidate for the integral test. If we were to use the integral test, then first we need to rewrite the function as f of x equals the a sub n term, which is 1 over x times ln of x squared. We need to check two conditions for the integral test. One, we see that 1 over x times ln of x is positive because n start with 2. For the second condition, it is simpler if we just simply take derivative and check that it is negative. Using the quotient rule, or we can rewrite it as x times ln of x squared to the negative 1 power. F prime of x is therefore, using the chain rule, negative 1 times x times ln of x, the quantity squared, raised to the negative 2 power. And then we still need to multiply the inside power, which is the product rule. 1 times ln of x squared plus x times 2 ln of x times 1 over x. Simplifying this, we have x times ln of x squared, the quantity squared in the denominator, and in the numerator we have negative, and then inside the bracket it is ln of x squared, x cancelled out, plus 2 ln of x. Inside the bracket is positive, but because of the negative sign, we see that the numerator is negative and the denominator is a square, so it is positive. This shows that the derivative is negative, which in turn shows that the terms 1 over n times ln of n squared, it is decreasing. So the condition for the integral tests are satisfied. We then integrate this from the starting limit 2 to infinity. 1 over x times ln of x, the quantity squared, dx. We do this by first let u be ln of x. du is 1 over x dx. We use a substitution. When x equals 2, u is ln of 2, and ln of infinity is still infinity. 1 over, we replace ln of x with u, so this is u squared, and then 1 over x dx is du. We don't need to integrate this because we recognize that this is a p integral with p equal to, which is more than 1. So we know that this integral converges. But if this integral converges, then the series also converges by the integral test. We conclude that the series n go from 2 to infinity of 1 over n times ln of n squared converges also by the integral test.